G'day chemistry students. In this video we're going to be covering dot point 3.3.1, 2 and 3. In particular we're going to be looking at how temperature affects reaction rate. Let's get into it. So first off, I want to sort of bring back some of the ideas that I talked about in the previous video on reaction rate. And I want to re-emphasize that you need successful collisions to have a chemical reaction proceed forwards for reactants to turn into products. And one of the ways in which collisions are successful is determined by whether or not the reactants that are present actually exceed the energy requirements for the reaction to move from reactants to products. And when we're talking about that amount of energy, we're talking about this activation energy here. So what you can see on the left is an energy profile diagram. We're going to be looking at those in significantly more detail in Module 4 and then again in Module 5 as well. For the moment, what's important is that we understand that reactants have a set energy and products have a set energy as well. But there is this step in the middle, some sort of hump that has an activation energy, an energy of activation, meaning the energy required for the particles that are reacting to have so that we can proceed from left to right reactants to products. Now, if we look at the graph on the other side, it gives us a slightly different visual representation of that idea. Now, what we have on this graph is an x-axis, which shows the kinetic energy of particles. And on the y-axis, we see the percentage of molecules that have that certain amount of energy. So, for example, if we look at the black line first, what we can see is that there are very few particles with low energy and very few particles with energy sitting somewhere sort of in the middle, but lots that exist in between. So most molecules here would have an energy at this point on the x-axis. And so that would represent the average amount of energy that those particles have. Similar thing for the red line. What we have are very few particles with low energy, very few particles with exceptionally high energy. The average point that we end up having here on this red line represents a higher energy than the energy seen here with our lower temperature. Now, notice, as I just sort of said, this black line represents particles at a low temperature, and this line here represents particles with a high temperature. Now, the idea here is that with low temperatures, particles have, on average, lower kinetic energies. Particles with higher temperatures have higher kinetic energies. And those kinetic energies are related to the activation energy over here. But what I want to talk about first is the idea that this graph demonstrates that not all particles are made equal. If you have particles, say a container of water at a set temperature, they won't all have exactly the same energy. The container of water might have an average energy, but on either side of this average, you're going to have particles with slightly lower energies and particles with slightly higher energies. And what we can end up doing is, at different temperatures, comparing the average kinetic energy of those particles. Now, what this graph shows here or represents is A, and that would be our activation energy. So what we can see is that for the red distribution here, for the higher temperature, we have a lot more particles which exceed the activation energy, whereas in the lower temperature graph, what we can see is much more few particles exceed the energy of activation. Now, as a result, what this is going to mean is that the higher temperature set of particles are going to have significantly more collisions which exceed the energy of activation, meaning that those collisions are going to end up yielding successful reactions. If you compare that to the lower temperature group, what that's going to mean is that those particles are going to have significantly fewer collisions which exceed the energy of activation, which means that there are going to be fewer collisions which result in a successful reaction. And when we look at reaction rate, the whole idea is the more successful collisions we have, the higher the rate of reaction. The less number of successful collisions we have, the lower the rate of reaction. So if we're going to take all of those ideas that I've just sort of begun to unpack in this section, what we can then conclude is that higher temperatures will yield reactions with a higher rate, and lower temperatures will yield reactions rates of reactions at a lower rate. Now, I also have a simulation to help visualize the action of the particles at high and low energy. So we're going to flip over there and have a look. Now, in this simulation, what we can see is that we have particle A and particle BC, and they react. Technically, this reaction is reversible. It does go in both directions. A and can react with BC, forming A, B, and C, and vice versa. And what we're going to be able to do is put these particles in a box, get them to collide with each other, and see when and where successful collisions lead to reactions. So what I'm going to be doing first is pulling this lever and allowing A to collide with BC. Now what we're seeing is as they collide, nothing is happening. They're coming into contact, but the collisions are not successful. And the reason is that the particles do not have enough energy to result in a successful collision. However, if we were to increase the temperature and as a result increase the energy of the particles, what we should start to see is one, that the particles might have a little bit more velocity. That's how it's represented in this diagram. But what we should be able to start seeing is that as we exceed the energy of activation, we're having collisions that result in a reaction. Now, it's a little bit hard to see because of where the particle is, so I might just quickly reset. I'll pull this one back. Actually, let's go with this one again. Pull this guy back so that we now have a total energy that exceeds the activation energy instead of is lower than. And when they collide, what we'll see is that the particles begin to react and swap places, which is exactly what we expect to see. Now, I can lower the energy again and decrease the energy to be below the energy of activation. And again, those particles will collide, but the reaction will not be successful. But again, raising the temperature, we're going to start to see successful collisions again. Keeping in mind too that if we increase the energy of the particles, and there's going to be more collisions occurring on average that will be successful and thus increase the rate of reaction like we were just talking about on the other slide. Now, in this version of the simulation, I'm going to be using an angled shot. And what this should demonstrate is that the orientation in which particles collide also has a very large impact on the success of the reaction. So if we look here down the bottom, we should see that A and BC react together to form AB and C. What that means is that A needs to collide into B to form AB, and if we were going in the reverse direction, C needs to collide into B to form BC. So if I collide A and B together, or the B part of the BC particle, they react, and that's all fine. And then after that, most collisions will be unsuccessful as they fly around in all different directions. But what we should be able to do is show as well that if we were to collide on a different part of the particle, just give it a sec to hit the center, that collision will be unsuccessful. So the orientation is another really important factor. Isn't really a factor for temperature. Note that the particles have more energy than actually, or they did have more energy than was actually required to have a successful collision, but that wasn't the only factor. The orientation was important as well. And this is where we're going to start moving into our next couple of videos on concentration and surface area to show that the number of collisions that occur will also greatly increase the chance of its successful collision and thus increase reaction rate. Thank you very much, everyone. In the next video, we're going to be looking at the relationship between reaction rate and concentration. But until then, have a good one.